you're pulling your notes up, I'm going to talk about the objectives. Objectives for today is, by the end of the notes, you should be able to distinguish between chemical and physical changes. Distinguish means tell the difference between. So you should be able to tell me if something is a physical change or a chemical change. Okay? Then you're going to need to be able to give evidence that a chemical reaction might have occurred. So we're going to talk about some things that are evidence or indications that something was a chemical reaction or a chemical change. And then finally, you'll be able to write a chemical equation and balance that chemical equation. We're going to talk about what it means for an equation to be balanced. Launching right in, let's talk about changes in matter. Matter can be changed in a total of 2 ways. The change can either be a physical change. Okay, during a physical change, there is no new type of matter produced. So whatever the substance was made of before the change, it's made of the same stuff afterwards. And only physical properties are going to be different. So if you remember from the lab we did with the periodic table, a physical property is a property of a substance that you can measure by looking at it or touching it, but without changing it. So I don't need to change an apple into a new substance to tell you what color it is, to tell you what shape it is, to measure its mass, to measure how tall it is, or how big it is around. Okay? That means those are all physical properties. So a change in any of those would be a physical change. An example of this is freezing water. When you freeze water, it goes from being a liquid, which has no shape of its own, to being a solid, which has a shape of its own, is harder, and sometimes the color is different, right? It goes from being clear and see-through to being white. But it's the same substance at the beginning and at the end. It's water when it's a liquid, and it's still water when it's a solid. So that is only a physical change. If, however, it is a chemical change, then at least one, but maybe more than one, new substances will be produced by the change. The physical properties might change, but the chemical properties definitely will change. So remembering back, a chemical property is a property of a substance that you can only observe if you change the substance. You cannot tell by simply looking at an object whether or not that object will burn. You might think you can, right? Because if I handed you a wooden chair, you would tell me, oh, well, this chair will definitely burn. But that's only because you have history with that object. If I gave you an object from an alien planet that you have never seen before and asked you if that object will burn, you cannot know without burning it. That's why flammability, the ability to burn, is a chemical property. You cannot observe if something is flammable unless you light it on fire, and in the process of lighting it on fire, you will change it into a new substance. An example of a chemical change is water breaking down into oxygen and hydrogen gas. You have to run electricity through water to do this because it takes a great deal of energy, but when you run electricity through water, it breaks the bonds between the hydrogen and the oxygen in the water, and then they form bonds with each other and you get hydrogen and oxygen gas. Water is not flammable. If I try to put a match to water, it will extinguish the match. However, oxygen and hydrogen gas are both flammable. So you can see that at the end of this change, going from being water to being gases, we have new substances, and we can tell that they are new substances because they have different chemical properties. Throughout our time learning about chemical reactions, you may hear me refer to a chemical change as a chemical reaction, and that's because those words can be used interchangeably. If something is going through a chemical reaction, it is going to have a chemical change happen to it. If you have something have a chemical change happen to it, that's called a chemical reaction. They are one and the same thing. So you may hear me use those words interchangeably. Signs of a chemical reaction. So when a chemical reaction or a chemical change takes place, there is sometimes evidence that it has taken place. You can definitely tell that the reaction has taken place if you look at the substances before and after and figure out if they are the same substance. Sometimes that's very obvious, right? Charcoal and wood are very obviously not the same thing, so you can tell that a change has happened because of that. But sometimes the end products might look similar to the beginning products, and so we need a little bit of a clue that a reaction has occurred. There are some signs that a reaction that's taking place might be a chemical reaction. Now, I want to stress that none of these are a sure thing, but they do warrant you investigating further. So, the first one would be a change in color. Sometimes chemical reactions cause a change in color of one or more of the things involved in the reaction, and as a result, this can be a sign. Now, as we discussed, sometimes things change color and there has been no chemical reaction, right? Like when water freezes, traps a bunch of gases in there and it becomes white. There's no chemical reaction there, so it's not a guarantee that a chemical reaction has taken place. It's just a sign that it might have happened. A change in odor. So if you notice that before the reaction it didn't have a smell and after the reaction it does, that can be an indication of a chemical reaction. The formation of bubbles, which indicates to you that a gas has been produced. Again, not always an indicator, because when you boil water, that's not a chemical reaction, but you are going to produce bubbles in the pan because some of the water is evaporating. However, when you mix vinegar and baking soda, you produce carbon dioxide gas. That is a chemical reaction, and those bubbles do mean that a chemical reaction has taken place. So you have to be careful with some of these. Formation of a precipitate. So if you take two liquids like we did yesterday, mix them together, and you wind up with a solid, that is a precipitate, good indicator of a chemical reaction. If the substance heats up or cools down, especially if it's a dramatic change, like it gets really hot or really cold, that's a good indication. And finally, releasing light. So when you burn something, it produces heat and light in the form of flame. Those are indicators that a chemical reaction may be happening. Now, I need to stress for you, again, that these signs may indicate that a reaction has happened. The only way you can know 100% for sure that a chemical reaction has taken place is if you test the substance's chemical properties before and after. If it has new chemical properties, so if it wasn't flammable and now it is, or if it didn't respond to light and now it does, then it is a new substance and therefore you have had a chemical change. If there are no new chemical properties, you have the same substance and no chemical reaction has taken place. Okay? All right, let's talk now about what's happening during a chemical reaction. New substances are being formed because the bonds of the old substance have been broken and now there are new bonds forming. Please remember from previous chapters that all matter is made up of particles, and those particles are constantly in motion. Even in solids, the particles are vibrating in place, so they are always moving. If those particles bump into each other, then they have a possibility of a chemical reaction taking place. Okay? But there has to be enough energy in the collision to break the bonds in order for a reaction to take place. Because if those bonds remain intact, then those atoms are stable, and if they're stable, they're not going to form new substances. They're not going to form new bonds. So you have to break the original bonds. Once you break those bonds, the atoms can separate, they can rearrange, and they can form new bonds with new substances. For example, if you break the bonds in water, then it splits into oxygen atoms and hydrogen atoms. And then those oxygen atoms can form bonds with each other, and the hydrogen atoms can form bonds with each other, and you're left with hydrogen gas and oxygen gas. So what this would look like is if you had some water molecules, right, and they're floating around in the water. okay? And then you have electricity run through that water, and it breaks these bonds that are between the oxygens and the hydrogens. Then that frees up the oxygens to form a nice little double bond with each other, and these hydrogens to form little bonds. And so you're left with H2 and O2 molecules, which are the basic forms of oxygen and hydrogen gas. So see how they are able to rearrange themselves once those bonds are broken?
Yeah.
Good. Scientists write out chemical reactions using something called a chemical equation, because sometimes we need to write these things down to pass information along. And if you're writing out the whole chemical reaction in words, it takes up a lot of space and it's clunky and it's hard to read. Whereas if we can write it out using symbols and things like that, then we have a much easier time reading it. So, a chemical equation is a description of a reaction using only the element's symbols and chemical formulas. To represent a solo element that's all by itself, we would use its symbol from the periodic table. So, for example, for copper, we would use the symbol Cu. However, there are some atoms that never exist all alone by themselves. We call those atoms diatomic. And what they do is they wind up bonding to another atom that is the same element that they are, and they exist out there with that element. So we write them as their symbol with the subscript 2. An example of this would be oxygen. If you are taking a sample of oxygen, you're not just going to find a bunch of loose individual oxygen atoms. What you're going to find is that those oxygen atoms have paired up, and they are in groups of 2 where they have bonded to each other, and then you have them floating around like that. So, oxygen is diatomic. We write O2 instead of just the letter O. If the substance you're representing is a compound and not a solo element, then we're going to use their chemical formulas. You can remember from the previous chapter that a chemical formula is the symbols of all of the elements that are in that formula, and then subscripts to indicate how many of each. It is important that you make sure all the subscripts in your formula are correct, because if your subscripts are wrong, you have the wrong substance. Okay, H2O and H2O2 are different substances, so you can't mix it up and have the wrong formula in your equation, or you will be telling people incorrect information. In chemical reactions, we split substances into 2 groups, and they appear on different sides of the arrow. Reactants are the starting substance in a chemical reaction. They're what you start with, and they appear on the left side of the arrow because we read left to right. Products are the substances that are produced, or your end products from the chemical reaction, and they will appear on the right side of the arrow. What we wind up with then is multiple reactants or products separated by plus signs, so that a general reaction looks like reactant plus reactant yields product plus product. If you have more than 2 reactants, you would just add another plus sign in there. And then that little arrow is the point at which the reaction is taking place. So when we read a reaction, we read that arrow as yields or produces or reacts to form. It's in the center of the equation. During chemical reactions, mass is conserved, meaning mass is saved. We talked about this already, but this is called the law of conservation of mass, which means the total mass of the reactants before the reaction is the same as the total mass of the products after. We have no new atoms. They are just rearranged. We don't create atoms. We don't destroy atoms. We just break bonds and mix them around. Nope, we need to talk about balancing equations now. Okay? Because a mass is conserved, chemical equations have to show that mass is conserved. Okay? Which is where we come up with the term balancing the equation. If you think about a set of balances, right? And you have more mass on one of them than you do on the other, they're going to be unbalanced. So when we talk about balancing an equation, what we're talking about is making sure that the same amount of mass is indicated on both sides of the equation. What that means is that if the mass is the same, we have to have the same number of atoms, and they need to be of the same type. So you can't have more of one atom on one side of an equation than on the other, because that would mean an atom was either created or destroyed, which we know does not happen. We're going to use the following steps to balance our equations. Step 1, write the unbalanced equation. Be sure that all the chemical formulas you include are correct. So what that would look like is, if you're writing the unbalanced equation, let's do the formation of water. We know water's formula is what? H2O. So we would write that on this side, and then since we're creating it, what atoms need to be involved?
2 hydrogen atoms.
Hydrogen atoms and
Oxygen atoms.
oxygen atoms. Okay, so this would be the unbalanced version of our equation, but we know that hydrogen and oxygen never exist by themselves. They're diatomic, so we would put a 2 on both of these to indicate that they are diatomic molecules, and we would find them in pairs. So this is our unbalanced equation. We'll come back to this in a moment. The next step is to count atoms of each element in the reactants side, so the left side of the equation, and in the product side, the right side of the equation. What you want to do is notice which elements, if there are any, that are already balanced, and which atoms are not balanced, meaning there's not an equal number on both sides. If all of the atoms happen to be balanced, then your equation worked out balanced already, and you don't have to take any further steps. So let's go back to our example and do that step. How many hydrogen atoms are on the left side of the equation? 2. How many oxygen are on the left? How many hydrogens on the right?
2.
How many oxygen?
1.
Just the 1. So,
Oh no.
which atom is balanced already?
The hydrogen.
And which one is not?
The oxygen.
Okay, so how would I go about balancing this to get the correct number of oxygen atoms?
Kill the oxygen one.
Can I do this?
No.
Why not?
Therefore, it's a different thing.
It's a new substance if I do that, right? We went from having water, H2O, to hydrogen peroxide, H2O2. So I can't do that. So there must be another way to balance the equation. What that looks like is the next step, which is to add coefficients in order to balance the atoms. A coefficient is a number you put in front of the element symbol or the chemical formula in the equation. What it does is change the number of molecules you have instead of changing the ratio of elements in the compound. So instead of saying we just need to add another oxygen to this compound, which we can't do, we're saying we need to add another molecule of water to make there be enough oxygen atoms. Okay. So in order to use coefficients, what you're going to do is you're going to pick one of the elements in the equation that isn't balanced, and you're going to write a coefficient in front of either that element, or if the element is inside a compound, you're going to write it in front of the compound to try and balance the number of elements. But what you'll notice is that sometimes when you do that, you go back and recount, and you'll notice that that's messed up another element. So if you change the number of one element and that unbalances another element, then you need to go in and add another coefficient in order to balance the now unbalanced element, which means this is really a process of trial and error. It's going to take some trying. And you're going to repeat adding coefficients until you are able to balance all of the atoms in the whole equation, and then your equation can be considered balanced. So, if we go back to our example,
Got it.
which thing do we need to put a coefficient in front of in order to balance the oxygens?
Oxygen on the right side.
So we're going to put it in front of the water molecule on the right side. So we can't What we can't do is we can't just come in here and stick the coefficient in here in the middle, because that would be like saying we're changing the number of oxygen atoms. So what we're going to do instead is we're going to put it in front here, and it's going to change more than one atom. It is going to go ahead and balance our oxygen atoms for us, because now we'll have 2 of them, but it's going to increase the number of hydrogen atoms that we have from 2 to 4. How could we fix this now?
Add 2 to the other side.
Yes, we're going to add 2 to the hydrogen on the other side, which is going to balance the hydrogens for us. And now we are completely balanced, and this equation is considered balanced. Okay, so see how changing one can sometimes unbalance something and you have to go fix it somewhere else, which is why this is really a process of trial and error, because sometimes you'll go through 3 or 4 changes before you get to the correct one. All right. This is where our notes end for today. You have homework. It's the check for understanding that should be posted now.